Now let's look at an example from Chapter 4 called Mart. Here's the setup. Mart Convenience Stores is working with consultants to better project what next year's sales will be based on 2019 data. The variables they collected data on were the amount of cars passing by each store daily. We'll call it traffic. The ease of entry into the store's parking lots on a scale of 1 to 100, with 100 being the easiest. The average annual income of homes within a mile of the store in thousands of dollars. And finally, the number of competing stores within 1 mile. Let's check the correlation matrix first. Sales is your Y value. So if you have a piece of paper in front of you, I typically put a Y above sales and then X's above all the other variables. Same thing down the side, Y, X, 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 X. Now, we want Y with X to be highly correlated. So sales has a correlation coefficient of 0.7043 with traffic. That's strong and positive. That's good. Ease has a correlation coefficient of 0.7003, also strong and good. Income doesn't look very strong. And then competition is the strongest. It has a negative correlation with sales. So as the number of competitors go up, sales will go down. Now, we next want to look to see if the X's are correlated with each other. That is that problem called multicollinearity. So when I look at traffic with ease, I find 0.8826. That's strong positive correlation between two X variables. Now, multicollinearity can cause several things to happen. It can mask a good predictor, like income. It can make the signs appear opposite of logic. I don't think that has happened in this particular place. And then we might also have redundant information because of multicollinearity. So now let's figure out what to do to fix that. We run a command in jump called Stepwise. So here you have the first part of Stepwise. After I've clicked on Go, you see that traffic, income, and competition are checked. Ease is not. And so in the end, when we look at the very best predictor, the one that comes in step 1, competition, is my single best predictor. R squared, if I used it alone, would be 72%. In combination with competition, traffic is the next best predictor. R squared goes up to 80.74%. Then income comes into the model, and R squared goes up to 83.05%. Now, ease of entry is entered in step 4, and R squared goes up automatically every time we enter an X. However, it says your best model occurs when R squared is 0.8305. So that means we're going to stop after income is entered into the model. Now we'll run the regression model with just those 3 predictors. First, we set up a hypothesis to test the overall model. I have 3 predictors, competition, traffic, and income. So I'll set 3 betas equal to each other and equal to 0. HA will say at least one beta is not equal to 0. To test the overall model, your test statistic is under analysis of variance, and it's the F ratio, 75.13. Its probability is less than 0.0001, Therefore, at least one of the variables is a good predictor. Now, under parameter estimates, you can test the individual coefficients. We'll do that with the t-ratios p-values. Again, ignore the intercept. Competition has a low p-value, less than 0.05. So does traffic, and so does income. So all three variables will be used in the model. Before I start predicting, though, I want to perform the residual analysis. Remember, the mean of the residuals is always 0 based on the nature of regression. When I look down the studentized residual column, I'm looking for any value between 2 up to 3, and that would be suspicious. And lo and behold, observation 22 has a studentized value of 2.8255. That is suspicious but not severe. I don't have to remove it from the model. None of the rest of the studentized residuals are large, so we'll go on to the next step. Another assumption about regression residuals is that they should be normally distributed. So most of my points are falling within these red lines, and it looks fairly normal since there's not a severe outlier. The last assumption, we called it randomness in Chapter 3, but in Chapter 4 in multiple regression, we're calling it homoscedasticity. That's what we want to see, a random shotgun type target for the residual plot. But what I see is very little variation on the left end, and it spreads out as it goes to the right end of the chart. Therefore, we have heteroscedasticity. This is a problem. It'll give us higher errors in prediction. So now our next step is to take the log of y and rerun the regression. Once I do that, my residual plot now looks much more random. If you see a bow tie, don't worry about it. Bow ties don't count in the plot for the residuals. But if I did have a less than, greater than, or a football shape, then I would not have taken care of heteroscedasticity. So here is Model 2. Notice under Summary of Fit, we have R squared now of 87.51%. That's better than our Stepwise model had used before we took the log of y. If I said compare the models, however, don't look at R squared first. Look at the root mean square error. The smallest root mean squared error, the better the model. So in Model 1, root mean squared error was 120.48. In Model 2, it's a little bitty 0.13. Therefore, Model 2 is better than Model 1. If I said interpret your root mean squared error, it would go in the sentence that says about 95% of the predicted log sales will be within plus and minus 2 times the root mean squared error, or plus and minus 0.26 units. Now we'll interpret the coefficient of determination and look at another problem that might occur. If I ask you to interpret the coefficient of determination, find R squared under Summary of Fit. 87.51% of the variation in log sales is explained by the model. The problem that might occur is sometimes we artificially inflate R squared. To check for this, we take r squared minus r squared adjusted, and we get a small value of 0.0082. If the difference is not close to 0.10 or 10%, then artificially inflated r squared is not a problem. We also had 3 predictors with 50 samples. The rule of thumb says we like to have at least 10 times the number of predictors for our samples. Therefore, 30 would have been sufficient to prevent artificially inflating r squared. Now find the regression equation. You can look in one of 2 places. Parameter estimates will always be given. Under the word estimate, you find your y-intercept. So start with what the y value is that you're predicting. Log of sales equals. Then put in your y-intercept, 6.63. Now keep going down the estimate column. Minus 0.2795 times competition. Then plus 0.00079 times traffic, and plus 0.00637 times income. This will be our model. Other times I could also put in the prediction expression for you. If you see EXP, that's telling you this is an exponential log model. So we have predicted the log of sales with the formula you see here. Finally, we're going to predict now. We've got homoscedasticity, no severe outliers, and the residuals are normal. So if I tell you that we're going to have 1 competing store in the neighborhood, a traffic count of 300 cars per day, and the income within a mile of the store is $47,000 annually. This will give us a prediction for sales in the red value over here on the left-hand side under Prediction Profiler. So our predicted value is 983.45. I have fixed the jump output so that it gives you the natural value and not the log value of sales. Then we can interpret the confidence interval for the mean sales given 1 competing store, 300 traffic count, and 47,000 income to be between 886 and 1091.61 units.